Welcome to an introduction to linear programming. In this video, we're going to look at what is linear programming. We'll then take a look at some key definitions and the fundamental theorem of linear programming. Then we'll use a few examples to cover an overview on how to solve linear programming problems. In the description below, you'll find links to several other videos on linear programming where I go more in depth on each of the steps that are used to solve linear programming problems. Let's get started. To understand linear programming, it's important to understand how it fits into the role of optimization in mathematics. So mathematics is a very large field, and one branch of mathematics is known as optimization. And this is where the goal is to find the optimal solution. Think of like finding a maximum or minimum value. Well, that field of optimization breaks down into two categories. There are linear optimization and nonlinear optimization. And linear optimization problems can be solved without using calculus, whereas nonlinear optimization problems require calculus to solve. So linear programming is nice because it allows us to solve optimization problems without using calculus, but it is limited in that it will not work for all types of optimization problems. Because linear programming falls under that branch of optimization, the goal of a linear programming is to find the optimal solution. These would be things like wanting to maximize profit, maximize investment interest, minimize cost, or minimize time, as in trying to minimize manufacturing time or minimize transportation time. Every linear programming problem consists of finding the maximum or minimum value of an objective function subject to constraints. The phrase linear refers to the fact that the highest power on any variable is 1. So for example, you could have a function such as p equals 20x plus 30y. If you notice, all of the exponents on these variables is just 1. If you had an x squared or a y squared or anything of a higher power, then typically you would use calculus to find the optimal solution. Let's take a look at a few more key definitions. Within this definition of linear programming, we see objective function and constraints. The objective function is the function that's to be maximized or minimized. A constraint is a linear inequality that must be satisfied by the solution to a linear programming problem. Constraints are usually going to be requirements or limiting factors. We must produce at least 5 items, or we only have enough material to produce at most 20 items. Constraints are always a requirement or a limiting factor that must be satisfied. Here are 2 examples of optimization problems. On the left-hand side, we're asked to maximize the function p equals 20x plus 30y. This would be our objective function since this is the function that we're trying to maximize. Subject to the constraints, x plus y is less than or equal to 7, x plus 2y is less than or equal to 12, 2x plus y is less than or equal to 12, x is greater than or equal to 0, and y is greater than or equal to 0. On the right-hand side, we're asked to minimize the function c equals 3.33x plus 2.00y, subject to the constraints 407x plus 271y is greater than or equal to 4,700, x is greater than or equal to 1, and y is greater than or equal to 1. So the objective function is always the function that we are asked to maximize or minimize. It will always be an equation. The constraints are typically always inequalities. Usually when we talk about constraints, that goes hand in hand with something known as the feasible region. The feasible region is the set of all possible solutions to the linear programming problem. The feasible region is the set of all points that satisfy all the constraints at the same time. In 2 variables, the feasible region is a portion of the Cartesian plane. Let me show you a few examples here. Looking at our first example linear programming problem, if you take all 5 of the constraints and you sketch the region in the Cartesian plane, you'll get this shape here on the right-hand side, which sort of looks like a triangle, but it's actually a polygon shape. This region here, shaded in blue, is known as the feasible region. Every point in that shaded region satisfies all 5 of those constraints. I have another video where I show you how I set up the feasible region using Desmos, available in the description below. We would say that this feasible region is bounded, and that is because there is a hard border on each side of this shape. Now let's take a look at the feasible region for our second problem, which is where we wanted to minimize the function c equals 3.33x plus 2.00y. If you take the constraints and you sketch the feasible region, you'll get this shape here on the screen. Now this region is unbounded. While there is a border on the lower left-hand side of this shape, truly the shaded area stretches off to infinity on the upper right-hand side. This region is called unbounded. The feasible region may be a bounded region, like the one on the left, or unbounded, like the one on the right. It's very important that we identify not only our feasible region, but also whether or not it's bounded or unbounded, because this is how we determine our solution to a linear programming problem. To determine our solution to a linear programming problem, we use what's called the fundamental theorem of linear programming. There are 2 parts to this theorem. The first part says if the feasible region is bounded, then the optimal solution for the objective function, the maximum or the minimum, will occur at one of the corners. In our first example, we saw that the feasible region was bounded. There are 5 corner points of this polygon that makes up the feasible region. Since this feasible region is bounded, the fundamental theorem of linear programming says that it will have a maximum or minimum, and the maximum or minimum will occur at one of those 5 corner points. The second part of the fundamental theorem of linear programming says if the feasible region is unbounded, like we saw in the second example, then a maximum for the objective function does not exist. Looking at this example feasible region on the right, it stretches off toward infinity. And so there is no maximum value that's going to occur because the feasible region just keeps getting bigger and bigger and bigger. It also says if a minimum exists, it will occur at the corners. Although this feasible region is unbounded, there is a lower boundary there, and if it does have a minimum value, it will occur at one of those 2 corner points of the feasible region. To summarize, if the feasible region is bounded, then an optimal solution for the objective function will exist, and it will be at one of the corners. If the feasible region is unbounded, then the objective function will not have a maximum. It could have a minimum. If it has a minimum, it will occur at one of the corners. That means that locating the corners of our feasible region is extremely important. Let's look back at our first example and identify the corners of the feasible region. Here was our first example problem, along with its feasible region. Using the graph, I'm going to identify the 5 corners. First, we have 0, 0, and then continuing in a counterclockwise fashion, we see the point 6, 0 is a corner, 5, 2 is a corner, 2, 5 is a corner, and 0, 6 is a corner. This feasible region is bounded. We have 5 corners, and the fundamental theorem of linear programming guarantees us that this function p equals 20x plus 30y will have a maximum at one of these 5 corners. So let's take our function and evaluate it at each of these 5 corners. To evaluate the objective function at each corner, simply plug the x and y value into the function. So for the first one, x is 0, y is 0, so we plug that into our p function. We would get 20 times 0 plus 30 times 0, which equals 0. Then plugging in 0, 6, we would have 20 times 0 plus 30 times 6, which equals 180. Entering 2, 5 in, we get 20 times 2 plus 30 times 5, which equals 190. Then entering in 5, 2, we get 20 times 5 plus 30 times 2 equals 160. Finally, the last one is 20 times 6 plus 30 times 0, which equals 120. Since the fundamental theorem of linear programming guarantees us that this function will have a maximum at one of the corners since the feasible region is bounded, look at our 5 function values to determine the maximum. It looks like our maximum occurs at the point 25, and the maximum value for p is 190. This is a brief overview of how to solve a linear programming problem. First, you need to write the equation of the objective function, then write each constraint as an inequality. Oftentimes, these will be done for you, like I've done in the 2 examples in this video. Then you'll need to locate the feasible region and identify the corners of the feasible region. Finally, you'll evaluate the objective function at each corner point. The solution is the corner point that optimizes the objective function. So if you wanted to finish out our second example, you would need to find the corners of this feasible region. For our second example, remember, since this feasible region is unbounded, no maximum value will occur. But that's okay because we're trying to find a minimum anyway. If a minimum value for this function occurs, it will occur at one of the 2 corners. In one of the videos linked in the description below, I show you how to identify the corners of this feasible region. But I'll just tell you here. The corners are 1, 15.8, and 10.91. Now that you know the value of the 2 corners, evaluate the objective function at those 2 corners. Then compare their function values to determine which one is the smallest. That's your minimum value. I'll let you take a look at that for right now. That's it for this video. Thanks for watching.